Welcome to Grand Rounds. I think we should get started. Today we have Dr. Matt Palmatier from ETSU. He's an assistant professor in the Department of Psychology. Dr. Palmatier got his bachelor's from Cal State University and master's and PhD from the University of Nebraska, all in psychology. And he's in the Department of Psychology, so I guess that makes you an unwavering psychologist.
Yeah.
So he previously was an assistant professor at Kansas State University before coming to ETSU in 2012. His research generally focuses on elucidating how drugs of abuse warp associative learning and create behaviors that are resistant to change. He's a highly productive scientist with over 40 published papers in his young career in very reputable journals like Psychopharmacology and Neuropsychopharmacology. Most recently, he's been funded by the NIH and the FDA to study how flavors modify nicotine abuse, which is, of course, highly relevant to our current growing problem of e-cigarette abuse. We're very fortunate to have such an outstanding scientist, behavioral scientist at ETSU, and we're very pleased to have Dr. Palmatier speak to us today. So please give a welcome to Dr. Palmatier.
Thank you. Thank you, Greg, for that introduction. I appreciate it. So we're going to talk a lot about nicotine today, and some of the data I'm going to show you are going to approach e-cigarettes and e-cigarette use toward the end. So the flavor stuff is coming. Be ready for it. I think I'm trying to go backwards. So I have no interest to disclose. I'm open to having conflicts if anybody wants to give me money, if that's available. I always like to start these things by thanking the folks in my lab. They do a lot of the work, and they let me take most of the credit, and so these folks are responsible for a lot of the data that you're going to see, and then these folks are responsible for letting me work on things at home at night, and they also keep me sane and a little bit grounded. So all the thank yous out of the way. A big research focus in our lab is the sort of the driving question is why do people smoke? And this question has sort of evolved over the years. And thank you for smoking. This sort of quote was a representation of they're cool, available, and addictive. And I think that was sort of true in the 1950s, 60s, and 70s. But since the 80s, it feels like culturally we've kind of had this understanding that cigarettes and tobacco are bad for you, and yet smoking rates have stayed about 15, they're 15% now, about 20% of the population smoking, and that was stable up until the last couple of years, and I think a lot of the drop-off has been in younger smokers, and they're just substituting e-cigarettes for tobacco. So we ask this question from the perspective of addiction as brain disease. So why do people smoke? It doesn't make any sense. We know cigarettes and tobacco are unhealthy. We know that they don't taste very good the first time you try them. Why do people start doing them? Why do people keep doing them? Well, if we think about why people keep doing them, the sort of brain disease model of addiction fits really well. The brain disease model is essentially just building on this idea that drugs are reinforcers. So if you smoke tobacco, you're delivering nicotine to your brain. Whatever nicotine is doing in your brain is causing you to smoke more tobacco. That's reinforcement theory, right? A bit circular, but that's how we explain it. More tobacco smoking means more nicotine in the brain, and those changes are being written on the brain. So whether you're self-administering cannabis and delivering THC to the brain, self-administering Red Bull or coffee and delivering caffeine to the brain, something about what that drug is doing in the brain is causing you to take more of that drug. And so in the brain, the specific changes that are taking place, we think are happening in this reward important for us a little bit later. So within the brain, where drugs are acting is in this incentive circuit, and the incentive circuit involves projections from the ventral tegmental area to the ventral striatum, or what we refer to as the nucleus accumbens often. There's interconnections with the ventral pallidum, the hippocampus, and the prefrontal cortex that become important also. These are big convergence zones. And this part of your brain is responsible for mediating incentive motivation, like I want to go to there. So all drugs of abuse act on it. This is an old graph from Nestler back in 2005, or an old figure, where he kind of identifies all of the different places within this incentive circuit. So if this is the projection, dopamine projection from the VTA to the nucleus accumbens, cannabinoids are working here, psychomotor stimulants like cocaine and amphetamine are working here, opiates are working here. Nicotine and alcohol you find in a couple of different places. You could also probably put nicotine at the terminal of those cells. But all drugs of abuse, all drugs that are changing behavior in these specific important ways that are causing substance dependence, are acting within the system in some way. And so that system is very important. It's important for incentively motivated behavior. That system evolved for us to do things that are naturally rewarding. And so these are some interesting fMRI data that kind of show what the system does sort of in a natural state without taking or self-administering drugs. So this is a nice representation from an fMRI study showing anticipation of glucose. So these are people who are in the scanner, and then you give them a little sip of glucose after they look at a cue, and eventually they start to learn that that cue is predictive of glucose, and so when they see the glucose cue, we get activation of the ventral tegmental area, which presumably is increasing dopamine in that circuit that I already mentioned. This is a beautiful psychology study about early stage intense romantic love. This one was a little bit more elaborate. To qualify for the study, you had to be in a relationship where you identified being in love with your partner, and you had to be less than 18 months into that relationship. And then you were looking at pictures of your romantic partner. And you were looking at pictures of attractiveness matched controls. And so what was happening is when you were looking at your partner, your ventral tegmental area would increase its activity more so than looking at a control picture that was matched on ratings of attractiveness. So this was really cool, but it's also, the psychology does some really great things like that, but then it also sort of emphasizes the worst in us. First of all, you can't have this intense kind of feeling if you've been in a relationship for longer than 18 months. And second, the increase in activity in the VTA was correlated with ratings of facial attractiveness. So the more attractive the picture was, the more the increase in activity in the VTA, which means that reward circuit is activated more if your partner is really attractive and activated less if your partner is an uggo. So another sort of negative on psychology. At the terminal region, so this is a ventral striatum, this is what happens when you're looking at pictorial smoking cues. So the same system is activating in the VTA for romantic love and for glucose, but it's also activating in response to smoking cues. So these are people who were looking at pictures of people smoking cigarettes, and these were dependent smokers, and we get increases in activity in the ventral striatum. So here you're activating the projection region, and here you're activating more the terminal region. But what drugs are doing, we think, is they're hijacking the incentive system, right? So this incentive system was built for us to do normal, natural kinds of incentively motivated behaviors, and it's getting hijacked by drugs of abuse. The more we take drugs of abuse, the more the cues for those drugs of abuse are hijacking the system. So I'm going to show you a lot of preclinical self-administration data today, and so it's important for me to get you kind of familiar with this preclinical model. And we think about it as being kind of this gold standard in abuse liability. If a drug is addictive, it should activate this incentive system, right? And to the extent that it activates that incentive system in the brain, it should be more addictive. So the drugs of abuse that humans self-administer should activate that system. That system is comparable in rats to what it is in humans. And so if we give the active ingredient in those drugs I mentioned before to a rat who has the opportunity to press a lever or make some kind of response to self-administer that drug, then that drug should activate the system and we should see the increase in behavior. So this rat, we let him lever press for nicotine. You can see he's in the act of pressing the lever. And when he presses the lever, this little cue light comes on, and then after about a second, all of the lights go off. But there's an infusion pump up here, you can't really see it, and that pushes nicotine through some tubing that is implanted into his jugular vein. So he can take an intravenous infusion of nicotine or caffeine or THC. Alcohol, we tend to let the rat self-administer it orally, but this is the gold standard. So we should be able to strip out nicotine, caffeine, alcohol, and THC and measure how addictive they are by measuring how much they increase behavior in the rodent model. Unfortunately, even though these are the 4 most widely self-administered drugs for their psychopharmacological effect in humans, it is almost impossible to get rats to self-administer them. We are one of only about 5 labs that consistently gets their rats to self-administer nicotine. We're the only lab who have gotten our rats to self-administer caffeine. No one else has published this. Alcohol takes a lot of work. Most people who do preclinical alcohol self-administration use selectively bred rats, high alcohol drinking, or alcohol preferring rats. They often include sweeteners in their alcohol. Sometimes they do things like intermittent access. Getting THC self-administration in preclinical models is incredibly hard. So far, it's mostly with non-human primates and mostly with second-order schedules of reinforcement. So people are taking these drugs, they're taking them for their pharmacological effect. Some of them we think of as being very addictive, and yet somehow they are difficult to establish as reinforcers in the lab. When we use them to activate the incentive system, something is going wrong. It's not working in the way that we think. And so I'm going to show you some old data. And I apologize for the way that this figure is showing up. It's old, and it was done in an old software system, and it's green and blue, and it's terrible for this lighting. I apologize, but believe me when I tell you that the things that are happening. So the things to focus on first here is that this is the number of responses. So on the y-axis, the number of responses that the rats are making for the drug, and they're responding for nicotine in this paradigm. So it's basically this setup right here. It was done in boxes just like this. And these open symbols at the bottom really don't mean anything. So these are how much rats just hit levers for nothing. So behind this guy, you can't really see it. There's a second lever in there. It doesn't do anything, and it just measures spontaneous behavior. So not much responding for nothing with the open symbols. The green triangles here represent rats that are self-administering nicotine with the cues I mentioned before. So when they press the lever, the cue light comes on for 1 second. After 1 second, the house light goes off and everything goes dark for a minute. And the reason we do that is to time them out. It was adopted from cocaine self-administration. It was to prevent them from overdosing and killing themselves with cocaine. And so that's what we thought was happening. So for the first 5 days, they make 1 response and they get a nicotine infusion. For the next 3 days, from days 6 to 8, they had to make 2 responses. They were on what we call an FR2. And you can see they increase their behavior. So it takes 2 responses to get a nicotine infusion. So they increase their effort. And then the rest of the days, they have to make 5 responses to get a nicotine infusion. And so they increase their amount of effort. They're sensitive to the change in schedule. With the cues. This blue line represents a group of rats, or these filled blue symbols, that are responding at the same lever for the same dose of nicotine, everything the same, except they're in continuous darkness. There's no cue light that comes on when they earn their nicotine infusion, and the house lights never go off when they earn their nicotine infusion. Nothing is different for them relative to this group, except whether or not the cue goes on, or the cue light goes on and the house light goes off. So if there's some environmental contextual stimulus in there, the rats self-administer nicotine. If there's nothing changing, when they take their nicotine infusions, they don't self-administer nicotine. Their behavior is very low, and it doesn't change when we ask them to change their effort. It's sort of fascinating. Well, think about the way that people self-administer these drugs, and it starts to sort of clarify. We beat our heads against the wall for a long time in my postdoc trying to figure out what was going on before we realized that it was hard to get self-administration of all of these drugs, and all of these drugs are self-administered in these complex chemosensory vehicles. So cigarettes are in tobacco. When it's combusted, there's over 4,000 chemicals in the smoke. Could include menthol, maybe other chemicals. Alcohol is self-administered beer. No one's mainlining nicotine, right? We're asking our rats to mainline nicotine. They're getting an intravenous infusion, and that's just not the way that humans self-administer the drug. Caffeine in coffee or in energy drinks, they come in these wonderful complex vehicles. Wonderful in the sense of coffee. I've never understood why energy drinks are as popular as they are from a taste perspective. And then we also found out that the cue itself was actually reinforcing. A lot of what the rats were behaving for in that first study was to turn the house light off. And so this study had a couple of goals. One of the goals was to try and dissect what is going on with the cue, because the cue became kind of an enigma for us. If the cue is there, rats will self-administer nicotine. If the cue is not there, rats won't self-administer nicotine. What happens if we give them the cue by itself? And so that's how we started this experiment. So then again, this is FR1, FR2, FR5. So the rats are changing, we're changing the schedule on them. But that we have two different groups of rats responding for two different things. One group is responding just to turn that cue light on. So this is the filled triangles down here. They're responding just to turn that cue light above the lever on. We were leaving it on for 5 seconds to be sure that they could see it, but we wanted to know if they respond for that cue light, will they like it? Will they respond just for that? And they weren't earning that many cue light presentations. This is reinforcers earned on this axis. How many times did they earn a presentation of it? And it wasn't that many. It was less than about 5 per session. And as we asked them to work harder, their desire to get the cue light went down. But the house light off, so we left the house light off for 30 seconds in this group. So there's a group of rats responding just to turn the house light off, and it's supporting more behavior. When we asked them to work hard up on the FR5, they were taking fewer house light off, so they weren't willing to expend a lot of effort in order to turn the house light off. But they clearly liked it better than the rats that were turning the cue light on, and they were earning more of them. In the next phase of the experiment, what we started doing was injecting the rats with nicotine or saline before the session. This is going to be a recurring theme. So half of the rats get nicotine, half of the rats from this group get nicotine before the session, the other half get saline, and the same for this group. And what happens is we find that nicotine increases responding for the house light going off, but not for the stimulus light going on. So the open squares represent the rats that are getting saline injections before testing, and they're responding to turn the house light off, and their behavior doesn't really change. The filled symbols are the rats that are getting a nicotine injection before the session, and then they're responding to turn the house light off, and they're massively increasing their behavior. So they like this, and nicotine is increasing their responding for it. They don't like this as much, and nicotine is not really changing their behavior for it. When we give them saline, they don't change. When we give them nicotine injections, they don't really change. They're responding for that stimulus. And that was exciting because it meant to us at the time that nicotine was enhancing responding for things that were good. So maybe what nicotine is doing in that incentive system that I outlined before is that it's priming it. It's getting it ready for the things that are in your environment that may be good in the future. So we confirmed with a bunch of different manipulations that these visual stimuli, if they were reinforcing, nicotine was increasing responding for it. We gave IV infusions that lasted the whole session, IV infusions that were separated from delivery of the visual stimulus. You could respond for IV infusions on one lever and the visual stimulus on the other lever. No matter how we did it, nicotine increased responding for that visual stimulus that was a reinforcer. In fact, we had to stop calling them cues because the rats liked them, right? So it's a cue if it means something good is coming or something bad is coming. But by itself, it was appetitive, it was appealing, it was something that they would respond for. So we started calling it a visual stimulus, but not non-reinforcing visual stimuli. We were able to show that nicotine would increase responding for sucrose. I'm going to show you some of those data in a bit. Nicotine would increase responding for saccharin. It increases responding for cocaine. If it's a thing that activates that incentive system, nicotine nicotine increases responding for it. Some other people also showed that nicotine could increase responding for condition reinforcers, and this is going to become a sort of thing I want you to pay attention to. So I'm going to give you an idea of what a condition reinforcer is. A condition reinforcement, or condition reinforcer, is jargon term, behavior analysis term for a thing that's good because it means something good is coming. And so I like to use the Christmas cookie candle example of a condition reinforcer. A Christmas cookie candle is a mean and evil thing to do to somebody who likes cookies, right? So I love Christmas because I love Christmas cookies. When I come home from work, for example, and it's Christmas time and I open the door and I smell Christmas cookies cooking, I am excited. That incentive system in my brain gets all pumped up with dopamine, and I go into the kitchen looking for cookies, and I find this. And this is not cookies. This cannot be eaten. This is as appealing as it is to people because it's a condition reinforcer. The smell of Christmas cookies baking has been associated with eating Christmas cookies in the past. So whereas I feel like this is evil and manipulative and a terrible thing to do to people who like cookies, other people enjoy it. I don't know why. I mean, I do know why, because it's associated with Christmas cookies. But that's essentially a condition reinforcer. This candle that smells like a thing that you want to eat is basically a condition reinforcer. It's activating your incentive system. And those are going to become really important to smoking, we think, later, and vaping. So maybe what nicotine is doing here, and here, where it's activating the mesolimbic dopamine system, depends on these other things in the environment. And so the drug is really important. I don't want to convey, because the stimuli are so important and that the environment is so important, that the drug itself, that nicotine, is not important. It is, because if you take the nicotine out of tobacco, there's no market for those cigarettes. People don't want to buy those cigarettes. Even as a therapeutic, when Quest cigarettes were marketed as a way to step down your nicotine intake and reduce your nicotine self-administration, they were commercially unsuccessful. In fact, NIH had to take over production of the Quest cigarettes because they're used as research cigarettes now for some of the dose reduction. The FDA is coming for your nicotine doses, by the way. And nobody drinks decaf unless there's a medical reason to drink decaf, right? And then near beer is only for when you're pregnant. So the drug itself is important, but maybe the drug is doing something in the incentive system to prime how the incentive system is responding to things. And if you think about drugs as stimuli, as things that are working on your brain, they also have this kind of contextual nature to them, right? We often get caught up, especially the behavior analysts in my field, we get caught up in this idea that a drug is a reward like food is a reward. And for cocaine, that may be kind of true, right? Cocaine's very short-acting, gets into the brain. It doesn't do a whole lot of desensitizing of receptors or upregulating or downregulating of receptors. So it's in your brain, it's working really fast, it gets out of your brain, and that's a lot like cookies, right? Like cookies get in your mouth, they taste really good, they go in your tummy, like 30 seconds. It takes me about 30 seconds to eat a Christmas cookie, and it's discrete, it's very short, right? It has a short time frame, has a short duration of action. Most drugs do not have a short duration of action, and they do lots of complicated things to your brain. And so historically, there's been this thinking about cigarettes and smoking and associative learning that's been just wrong. And the idea has been we get thousands and thousands of conditioning trials with nicotine. Every time you smoke a cigarette, a puff gets into your brain, it changes your brain, and everything that's associated with that puff then becomes better. And when that happens thousands and thousands of times during your lifetime, you become addicted, dependent. All those cues become important and better. So it's this bolus idea. You get a spike of nicotine to your brain, and it's there, and then it's gone, and then your next puff, you get a spike of nicotine to your brain, it's there, and it's gone. But nicotine is much more contextual than that. So Jed Rose, who's down at Duke, did this really cool study showing that nicotine is actually not getting into the brain and producing a spiked bolus. So what he did was he took dependent smokers, so that's the pink line, the DS, and non-dependent smokers, so that's the blue line, the NDS. So non-dependent smokers are people who have smoked more than 100 cigarettes in their lifetime, but they're not daily smokers. They don't meet the criteria for dependence. And then your dependent smokers are your hardcore, like pack-a-day smokers who have to smoke all the time, definitely meet the criteria for dependence. So he loaded their cigarettes with 11C nicotine, which allowed him to put them in a PET scanner and measure the time course of nicotine in the brain, because he could detect irradiated nicotine. And so what he found was that both in your dependent smokers and in non-dependent smokers, nicotine was getting in after one puff. So this is what happens after a single puff. It's getting into the brain, and you're getting big increases in nicotine content in the brain. But those big increases, even after a single puff, are hanging around for 10 minutes. 600 seconds is a long time. So even after a single puff, you get this big elevation in brain nicotine, but that big elevation in brain nicotine does not go away. You're not getting this spiked bolus that we thought. So this was with 10 puffs and a 48-second inter-puff interval, so they controlled kind of how much the smokers were puffing on these cigarettes and how long of a break they were taking between puffs. And you can see same time frame at 10 minutes with 10 puffs, you get small elevations in nicotine intake with each puff, or in brain concentration with each puff, but it's hanging around for a long time. So whether it's 1 puff or 10 puffs, your brain nicotine content is elevating over time, and it's hanging around for at least 10 minutes. And in dependent smokers, it's actually lower than in non-dependent smokers, because the nicotine's getting sequestered in the lungs. So your dependent smokers have a bunch of tar and gross things in their lungs, and that's where the nicotine is being sequestered. So even if you're a dependent smoker, that just makes it more contextual, right? The more nicotine is being sequestered in your lungs, the slower it's getting to your brain, the longer its lifespan, if it's lasting like 10 minutes, the more contextual it is. I don't want you to think about nicotine as this spiky thing that gets into your brain, makes you go, oh my gosh, that's amazing, and then goes away. It's much more contextual, and it is, we think, maybe moderating or modulating your responses to stimuli in your environment. So there's a lot of things to not pay attention to in this slide, but what we think is happening with nicotine, and this is what kind of kicked off my research program, is that the incentive system is becoming primed for motivating appetitive stimuli. Your incentive system after you smoke a cigarette is becoming primed for anything good that might be in your environment, and so things that are positive might be more appealing. So my research program has kind of 2 main directions. What is amplification? One question is, how does that work? So one direction is what is the mechanism of this? How does this amplifying effect of nicotine work? What does that mean for behavior? And what does that mean for the systems of the brain that control approach behavior and appetitive motivation? And then another question is, well, how does that lead to smoking? Because it's great if nicotine primes your brain for things that are positive, but what about your first cigarette is positive? Any of you who have smoked, and I will freely admit to having smoked cigarettes in the past, that first cigarette is a very memorable experience, but not in any kind of good way. It surprises me to no end that people smoke a cigarette the first time. Some people throw up, many people get dizzy, many people are nauseous, and then they go, yeah, I want to do that again. That seems like a thing I should do twice, right? For many people, it is not a positive experience. For me, it certainly wasn't. So the first thing I'm going to tell you about is kind of mechanism. And mechanism is how is nicotine amplifying behavior? And so when I think of amplifiers, like for me, when I think of amplifiers or something that may amplify incentive motivation, I always get the picture of like Back to the Future. For some of you, you might be too young for this, but the beginning scene of Back to the Future, Marty McFly goes into Doc Brown's house, and he gets his guitar, and he stands in front of this massive amplifier, and he strums the guitar, and the amplifier blows him through the wall behind him. But there has to be input, right? In order for something to be amplified, it depends on the input that's coming in. When the vibrations in the guitar get amplified through that amplifier, there's a big enough gain that it pushes Marty McFly through the wall that's behind him. So it occurred to us that if sorry, I went too far. That if nicotine was amplifying incentive motivation, then the input might be important relative to the output. So we didn't know why lights were reinforcing to our rats. We had no clue why lights might be reinforcing to our rats, but we do know why sugar is reinforcing to rats. It's because it tastes yummy. And so what we decided to do was to manipulate the input of a reinforcer that we could manipulate systematically. And so what we did was we gave the rats a bunch of different concentrations of sucrose. So half of our rats are getting injections of nicotine before the tests, half of our rats are getting injections of saline before the test, and then we measured their behavior at a bunch of different concentrations of sucrose, thinking down here, down at the 2.5 and 0% sucrose concentration, we shouldn't be getting any amplifying effect of nicotine. If there's no input, there should be nothing for nicotine
have your attention, please.
to
Rapid
amplify.
responders, 6,300. Rapid responders, 6,300.
Okay. Hope everyone's okay. So what we anticipated was getting something like this. As the sucrose concentration goes up in our saline rats, we expect their motivation to increase. So these data kind of represent motivation. And so I have the rats on what we call a progressive ratio schedule, which just means it's kind of a jerk move. Every time they earn sugar, we make them work harder for their next sugar delivery. So if they make 2 responses and they earn a sugar reward, the next time they have to make 4, the next time they have to make 8, the time after that they have to make 16. It increases at an exponential rate. By doing that, they can't just satiate themselves on sugar. They can't take so much sugar that they just get full and happy and go, I don't want any more sugar. They keep working for it, and they keep working for it until the effort required outweighs the sugar reward. And when the effort is, I have to make 30 or 40 responses to get one little taste of sugar, they give up. And the saline rats, when they get to about 25 responses for a little taste of sugar, even if it's 60%, which is like syrup, it's too much for them and they stop responding. When we inject them with nicotine before the session, we get this massive increase in their responding. And this is what we predicted. When the reward is real good, nicotine, if it's amplifying it, should make it even better. But we thought that as we dropped the concentration of sugar, if the reward was not as good, then nicotine should not be increasing their responding as much. And that's not what we got. What we got was that it didn't matter how good our reinforcer was. It didn't matter how strong our sucrose was, how good the sugar was. Nicotine just increased the amount of effort the rats were willing to make. They could reduce their behavior when the sucrose concentration dropped. That was very clear, but it was enhancing responding out here just as much as it was enhancing responding there. So even for 0% sucrose, the rats were food restricted, not water restricted. There's no reason they should love water, 0% sucrose, but they were still showing us a significant increase in responding. One concern in that study was we were letting the rats nose poke for sucrose. So they were pressing this little nose key, and they were getting sucrose here. And all the rats got 60% and then 40% and then 20%. And so they all got sucrose, and they had sucrose for a while before we started dropping the concentration out. And so we realized we weren't in control of the cues. We weren't in control of the things that predicted that sucrose was going to be available, right? So back to that Christmas cookie candle. We were not in control of that because it was the same rats getting every concentration of sucrose. So what we did was we split them up again by nicotine or saline injections before the test session. But now we had groups that only responded for no sucrose at all, 0%, only responded for 5% sucrose, or only responded for 20% sucrose. And those 3 different concentrations, that was all you ever got. So the cues were always only associated with nothing, a small concentration of sucrose or a high concentration of sucrose. And when we did that, we found exactly what we predicted. If the rats always responded for water, 0% sucrose, and it wasn't reinforcing, injecting them with nicotine did nothing. If 5% sucrose was more reinforcing than water, but not by much, and nicotine enhanced responding for that just a little bit, and 20% sucrose was much better than 5% sucrose in our saline groups, and nicotine enhanced responding for that substantially. So the amplifying hypothesis kind of worked. If the reinforcer is not that good, then nicotine doesn't enhance responding for it. But if the thing is better, then nicotine does enhance responding for it. It just didn't work in the way that we expected, because what happened was this gave us the idea that this is more about incentives that predict deliveries of good things, more so than the good things themselves. So if you go back to this graph, the rats are clearly able to detect a change in concentration of sucrose. Putting them on nicotine did not make them stupid, it just made them more motivated. Why were they more motivated? Maybe they were closer to the nose poke, maybe they liked it, maybe the nose poke drew them in more, maybe the receptacle drew them in more, but they made more responses. When that receptacle and nose poke didn't mean as much, then we got no effect of nicotine, when that meaning was limited. So we figured there was a way to directly test this. Our hypothesis was it's not the sucrose that nicotine is enhancing, it's the anticipatory cues. And if it's the anticipatory cues, if it's the things that predict the rewards, then we should be able to measure that. And so we use this Pavlovian conditioned approach paradigm. And Pavlovian conditioned approach, PCA, is pretty straightforward. So this is kind of a schematic of what the rats are doing. And these two little gray blobs over here represent receptacles where the rats can go and stick their head. And so inside of those receptacles, we can deliver two things. One thing we can deliver is a cue. We turn on a light for 15 seconds, and that's going to be represented by that receptacle turning yellow. And then at the end of that 15 seconds, we can deliver a sugar reward, and that's going to be represented by the receptacle turning red. So the cue comes on, it's on for 15 seconds, and then it turns red. That just means that the sucrose has been delivered. The rat doesn't have to do anything. The rat could sit here the whole time and just watch this play out and then go get its sucrose. But what they tend to do is they tend to approach the receptacles, and they tend to stick their heads in there and investigate while the cue is on. And that's very reliable behavior, and it's easy to measure. But we thought if this is what's important, if nicotine is enhancing approach, it's enhancing what that anticipatory cue is doing, then if we pre-treat them with nicotine, then we should see an enhancement of that anticipatory approach. Or if we pre-treat them with saline, we shouldn't see that. So we used a few different concentrations of sucrose because we're really good at making this behavior robust, and we're really bad at weakening it. Long story short from this graph is nicotine didn't do much. So at 20% sucrose, nicotine didn't increase their conditioned approach. At 5% sucrose, we saw like a little trend for nicotine to increase their conditioned approach relative to saline, but it wasn't by much, and it wasn't statistically significant. And then if they're getting 0% sucrose, they're not making much conditioned approach. So this is a nice control for like, they don't care about the CS because it doesn't mean anything. So we thought, well, that sucks. Didn't do what we expected it to do. We really thought at 5% sucrose we would see kind of an effect of nicotine, but that there would be a ceiling here. And so this is just an entry score measure that I'm showing you. How much do they approach during the CS relative to a control period during the session? So we thought, well, let's take away sucrose. If we weaken their behavior, maybe the nicotine rats will perseverate a little bit longer. Maybe they'll maintain their conditioned approach, but it didn't. So in this second phase, what we did was we kept giving the CS, we kept turning on the cue light, but we stopped giving sucrose. And when we stopped giving sucrose, everybody reduced their responding, and the nicotine rats weren't stupid. They continued, just like they learned very well that the cue meant that that sucrose was no longer coming, and they didn't go sticking their heads in the receptacle for no reason at all. So we threw the entire behavior analysis, the Pavlovian section of the behavior analysis textbook at these rats. A spontaneous recovery test is kind of like a relapse test. A reinstatement test is kind of like a relapse test after extinction. We did get some effect on reinstatement, but I don't want to focus on that too much. We get reacquisition, and nothing really happened. It looked like something was happening here, but nowhere else. We didn't know how to interpret that, so we went back to the drawing board. We had two receptacles in the chamber, and we realized that this receptacle had been associated with sucrose a lot. It had the cue being delivered in it. It was associated with sucrose a lot. So we thought, what if we just change which receptacle the sucrose is being delivered in?
May I have your attention, please? Rapid response to 4200. Rapid response 4200.
So So the Q is going to come on the right side where it has always come on, where it's been associated with sucrose in the past, and then sucrose is going to be delivered over there. And this is what we call in Pavlovian conditioning a sign tracking, goal tracking paradigm. So sign tracking is how much the rats stick their head in this receptacle. When the Q comes on, how much do they go over and look at the Q? How much do they go over and stick their head in the receptacle where the Q is delivered? And goal tracking is how much did they stick their head into that receptacle, right? If the Q comes on and it means in 15 seconds you're going to get sugar over there, the efficient, smart behavior is to go over there and wait for the sugar, right? The smart thing to do is to wait over here. So sign tracking is how much they're sticking their head in the receptacle where the Q is delivered. Goal tracking is how much they're sticking their head in the receptacle where the sucrose is delivered. And you can see with the saline rats, with 0%, again, nothing's happening. With 5% sucrose and 20% sucrose, the saline rats have shifted. Instead of sticking their head in the receptacle where the CS is, they move over to where the sucrose is being delivered. Again, with the 20%, they also move over. But the nicotine rats perseverated on the sign. When the Q came on, they could not stop going over and sticking their head in the receptacle for where the Q was being delivered. When there was a Q that anticipated sucrose delivery, the nicotine rats had to interact with that Q. They perseverated on that Q. So we replicated this a few times, and it's a pretty consistent finding in our lab. When we give a Q in one location and sucrose in another location, nicotine massively increases approach to the Q. It massively increases sign tracking. Sign tracking behavior has been associated with increased cocaine self-administration in rats, hyperactivity, and a bunch of other things. So I'm going a little longer than I intended. I apologize. So that was the mechanism side. So we do have pretty good confirmation, we think, that it's anticipatory cues. It's anticipatory cues. It's the things that predict the things that are good that nicotine is acting on. It's making those things better. But nobody's smoking sugar. We've been doing all these studies with sucrose. Nobody's smoking sugar. We're seeing nicotine increase behaviors that are motivated by sugar, or motivated by cues, I should say, that are associated with sugar. But sugar is complicated, and it's not telling us about how this is playing back into smoking. But there are anticipatory cues in tobacco products, and I would argue that there are anticipatory cues in vape products. So if you look at any Marlboro cigarette, whether it's red or gold or silver, 100s or 25s or 72s or 27s, NXTs, craft blends, Virginia blends, cigarettes have two sets of ingredients in them. They have the casing ingredients and then the top dressing. And the casing ingredients all include these conditioned reinforcers: licorice extract, cocoa, and cocoa products. There's tobacco, there's water, there's sugar in there, but these are anticipatory stimuli. These are stimuli that most people have experience with before they ever smoke, that are in every single cigarette, whether it's Marlboro or Camel or whatever your cigarette brand. These two ingredients are very common in the casing ingredients for cigarettes. Menthol is another thing the FDA has decided to look at. Menthol is a classic condition reinforcer. I know from experiments on my kids that were not IRB approved, but I will never publish, so it's okay, that we don't naturally like menthol. So they had some gastric issues early on, and the pharmacist covered the medication with mint. And I was like, well, why would you assume that they would like mint? And he was like, it's mint. Everybody likes mint. And I gave it to them, and they made this response of they were newborn babies. They hadn't had anything else except milk. They really did not like the mint. That's confounded because there was medicine in there, but they really didn't like the mint. And I was like, haha, they don't love mint. Nobody loves mint until this happens. All of this has to happen to make you like mint. And now that I have young kids, like getting them to brush their teeth and stuff, I'm starting to realize there's a lot of sugar in kids' toothpaste, which just seems like it's keeping dentists in business, right? Like you put sugar in kids' toothpaste. Bad. Nobody likes mint until it becomes a condition reinforcer. So how are we going to model that in the lab? Well, let's give our rats a bunch of sucrose in their mint. So what we did was we turned menthol into a CR by giving our rats an hour a day to drink sugary mint. And so we had two groups in here. The paired group, they're going to become the CR group a little bit later, so I should have changed that label. They're drinking mint and 20% sucrose. And then the unpaired group, they're drinking grape Kool-Aid and 20% sucrose. But the unpaired group is also getting mint. They're just getting it in tap water. And they tell us, yeah, the mint is not that good. The paired group is also getting grape Kool-Aid. They're also getting that in tap water. So it was essentially a discrimination. Half of these rats learned to really love mint. The other half of these rats learned to really love Kool-Aid and not care so much about mint. Then we are going to let them self-administer nicotine. Some of the rats, we're going to let them self-administer nicotine with mint. And all the rats, I should say, are going to self-administer nicotine with oral menthol and water. And so what happens is the rats go into the operant box and they have two sippers that they're presented, an active sipper and an inactive sipper. When they make licks at these active sippers, so we can detect when they're touching the sipper based on current running between the floor and the sipper, when they make licks on the active sipper after 2, 5, or 10 licks, we turn on a little valve here, or we open a little valve here that drips menthol, unsweetened, no sugar in it at this point, unsweetened menthol into the sipper tube, and they can drink that little bit of menthol that's dripping out of there. And then we also give them a nicotine infusion. On the other side, when they meet the schedule of reinforcement, when they make their responses at the sipper tube, they just get a little water dripped into the sipper tube. So it's essentially an active response and an inactive response, and they're taking nicotine with menthol that now is yummy because it's been associated with sucrose, and those are the CR groups. Or menthol that's neutral because it's been associated just with tap water in the home cage for many, many days. So what happens is, the axes on these graphs this must be a PC to Mac translation. Sorry, so you're just going to have to trust me. The nicotine dose we were using was really low, 3 micrograms per kilogram per infusion, and it didn't support any behavior. So these are the rats that got menthol, neutral menthol, and nicotine, and they just didn't do anything. The square symbols here are the rats that got menthol paired with sucrose and saline infusions. So menthol was a condition reinforcer. They licked for it. That licking kind of went away after a few sessions, but they didn't respond much for it. But when menthol as a condition reinforcer was delivered with nicotine infusions, we got these massive increases in their behavior. So if we give them nicotine with a thing that's predictive of reward, that's been paired with sucrose in the past, then that thing interacts with the nicotine to massively increase their nicotine self-administration. So if you're self-administering nicotine by itself, like let's say a vape with no flavor and just nothing, then that's not going to necessarily be as good as if you're self-administering a vape with maybe blueberry or maybe some other combination of flavors that have been associated with dessert in the past, which is happening all the time. So with licorice as a condition reinforcer, we found a similar pattern. At low doses, we got a big increase in self-administration. As our nicotine dose went up, the pattern was that they came together. So these rats self-administered nicotine in the neutral group. So if licorice wasn't associated with sugar, they still self-administered nicotine and there were no differences. But when we pushed them, when we used that progressive ratio schedule to measure how motivating licorice and nicotine were, that's when the high doses separated. So this is 20 micrograms per kilogram per infusion, and this is 40. When we forced the rats to make more effort, at these doses, the nicotine and the condition reinforcer kind of synergize, kind of work together to make the rats make more effort for the nicotine. The last graph I'm going to show you is when we punish the rats, if they're at the highest dose, when we punish them by sticking quinine into the oral solution, it punishes rats responding for nicotine and a moderate dose of nicotine with the licorice condition reinforcer. So the quinine, the bitter quinine, causes them to reduce their nicotine self-administration. But if they're at the highest dose of nicotine, if they're self-administering a lot of nicotine, they maintain a higher rate of responding. So even though they're getting licorice with quinine in it, and this concentration of quinine, 1 micromolar, tastes very, very bad, I promise, they're still willing to drink that quinine with the licorice in order to get their nicotine. So it may be, but only if the licorice has been a condition reinforcer. If the licorice was neutral, we're still seeing a reduction in their responding for nicotine at that high concentration of quinine. So we can punish them out of taking the nicotine, but not if licorice has been a CR in the past. The CR and nicotine also increase incentive and extracellular dopamine in the incentive system, but again, the axes are kind of spoiling that story, and it's toward the end, and I know you're tired, and I told you a lot of things about flavors and CRs and anticipatory stimuli, but your takeaway, if it's this: when you're smoking or vaping or whatever it is that you're doing to self-administer nicotine, that nicotine is not being delivered in a vacuum. It's being delivered with stimuli that may or may not have incentive value. That they're probably not neutral. Some of them may seem like they're disgusting. Some of them may be really good. And they may be activating that incentive system of your brain. And so if nicotine is priming the incentive system of your brain, which I hope I convinced you of, and you're getting these other things with your nicotine, that those two things may be combining to produce this like why people smoke kind of response. Like when those things are delivered together, that may explain why your behavior increases as much as it does. And so if we took the flavors out of tobacco smoke, I don't know if people would stop smoking, but I would bet that they would. If we made people vape only nicotine and PG and VG or whatever it is that they're using to mix those solutions in, and not blueberry and strawberry and pineapple and pina colada, which is what all of the vapes are, maybe they probably wouldn't vape as much. So if those flavor additives weren't in there, if those condition reinforcers from your past were not in those products, I don't think that they would increase behavior as much as they do. And thank you for your time. I have time for questions if anybody has questions. Yeah.
This kind of leads to the question is what was the original motivation for putting menthol in tobacco products, and what then is now the motivation to put flavors in the vaping solution? Is it based on science?
No, it was based on how people took the smoke. So because of the settlements with the tobacco companies, a bunch of their documents had to be revealed. And if you look at their old focus groups they did with people who were smoking menthols, they said that they liked the menthols because they tasted like peppermint patty. They made the smoke taste smoother. It was less harsh. They also said they wouldn't smoke if there was no menthol in their tobacco product. So they said, without menthol, I would not be a smoker at all. So the tobacco companies the FDA is really starting to think about taking menthol out of cigarettes, and tobacco companies are fighting it because it's like 25% of all cigarettes sold in the United States are menthols. And so I think that group of smokers is maybe sensitive to the harsh taste, but maybe also they really like mint. Like my daughter loves mint chocolate chip ice cream, and it scares me. To think that thing is so good, and that if nicotine is sort of priming that particular taste and that particular flavor. Some people just really like mint. Like some people eat Tic Tacs and they always have mints on them or whatever. And so I think that historically it's been a recipe, and all the flavor ingredients have been, how do we make the smoke taste better? And they just capitalize on flavors that we already know from food additives. For example, there's like a beaver gland extract castoreum. It makes vanilla taste stronger, and raspberry and strawberry. And the food industry knows about this. And so tobacco companies use it in tobacco products that have like vanilla and other flavorings in there, because it enhances those flavors and the perception of those flavors. So I think most of it has been, how do we make it taste better? While they were making it taste better, what they didn't realize is it tastes better because it's activating the incentive system of your brain, and nicotine may be interacting there. Does that make sense? So with vapes, I think it's just because otherwise you're inhaling, vegetable glycerol and PG, whatever that vehicle is. Those have a little bit of sweetness to them, but by themselves, they're not going to be very appetitive. And nicotine does have a taste. You have nicotinic cholinergic receptors in your airway, and so smokers can tell when they're smoking a denicotized cigarette, partly because it feels different. It doesn't have the throat hit And so for vapes, there's some of that. And then for, it's mostly, I think, just commercial, like how can we sell more of it? And how to sell more of it is to make it taste yummy. But I think that's also how to make it more addictive also, given our data. Anybody else? Well, thank you guys for coming. I enjoyed doing that, so
Thanks very much.
have a good afternoon. If you're here for a speaker series, you can bring me your sheet and I'll sign it for Psych Speaker Series.
That's actually not long.
Okay.
So my daughter